Everyone, today we are going to do a Cses problem, that is minimal grid part. We are given an n cross n grid whose each square contains a letter. We have two options, either to move right or to move down. Now what we have to choose there, we have to create a lexicographical minimal string that we can construct, and we have to go from the top left to the bottom right. Now at the first glance this may seem as a standard DP problem, but it is. The only catch is here it's a constraint. What we can do is the standard DP problem, like we can create a DP of I comma j, and we can store the string out here. Here DP of I comma j means that from a given point I comma j, what is the lexicographic string from here to the bottom right. But the issue with this problem is that the constraints are too tight for that. Like if n is equal to 3000 into 3000, and the string size would be around 3002, it may be of n, order of n, because like for example we are choosing like this. For example, this is the string, so in that case it's of O of n cube solution, and it wouldn't give TLE, but it would give memory limit exceeded in the first glance, and when you submit this code it will give a memory limit exceeded. To resolve that memory limit exceeded, what we could do in our initial approach, what are we doing? We are storing the string. This is the problem. At every index we are storing the string that is lexicographically smaller string from that index to n-1, m-1 to the bottom right. What if there is a way to remove that whole string storage? What if we don't store the whole string, but during the answer construction we have to construct an answer? During the answer construction we are able to do that without actually storing the whole string. There is a way. Like for example, if I take this test case A. Now the main motive that if we are at this element, if we are at this index, we have two options, either to go from here and either to go from here. Both are B. Then what to choose? Like if we start from here, we can go to A or we can go to B. The most probable thing would be to go to A, because we have to create the minimum lexicographical. But if we are starting from this A, there are two choices and both have a starting B. So we need to see that from this B, what is the index that I'm creating. Like this B has a part to go from this C to this index and to this index. Similarly, this has a part to from this index and to this index. And if we clearly distinguish that if we group the element along this diagonal, this whole element are the deciding factor. After this, to choose which B we have to go forward, this diagonal is the deciding factor. Now at first this approach seemed to be a little non-intuitive, but I read an article about it in Code's blog, and he cleverly mentioned that why are we grouping these diagonals. So if you can see around here, this elements on this diagonal would require information from this diagonal, the next diagonal. Like element present in this diagonal, this A, B and C, would only require information from this diagonal, not from this diagonal. So let's just backtrack. We would start from A and go towards this, and would comply an answer. We would make an answer. So this A, we can't go over here, we can't go over here, means that means that if we are at a particular index, if we are at a particular diagonal, like for example this, we are at this diagonal, we need information from this diagonal. So we can group elements based on their diagonals, and assign a rank to it. Now what do I mean by rank? Rank is something like if we are at this and I need information to where to go, there are two choices around here and around here. One is A and one is B. So that's pretty self-explanatory that we will go towards A because A would give me the lexicographically smallest string. But what if I have A here and B and B? Now what, like in this case, we have A here, we have B here, B here. Now at this position I have to think, I have to verify that which B should I go towards it. Which B should I go towards it? So it would lie on the same diagonal. Above there would be a different diagonal. Now this B would take information from element at here and element at here. Similarly, what element from here and element from here, it will take information. From this part we can take only one element. Now if we can store a value that which element is most accessible from which element is most accessible from this position and from this position, this two information would be able to decide which B should I choose. Which B should I able to choose? Okay, just let us do a simple diagram. So if we are at this position, this is the starting point, this is the ending point, so we couldn't go forward. So which means that I'll store that element and the rank of it. The rank is basically the first rank. The element is A and the rank is the first rank. Okay. Now if I'm at this position would require two things, here and here. We don't have any element here, so we can do some padding around here. That padding would store any element. If try to access this region, we would store a number and infinity. Infinity means the rank. The higher the rank, the less important that number is. And now this, what's the rank of this? The rank is 1. The rank of this element is 1 and it's infinity, so we will be storing 1. Now what 1 is? 1 is the best rank of its children. Its two children is around here and around here. This doesn't exist, so we are storing infinity over here and 1 is the rank of this. Now in here, similarly we'll do the same thing from here. Infinity for this, and the rank of this is 1, so 1. Now we have two things, A and C in this diagonal. One may wonder that we have A over here, C over here. The best rank of its children is 1 and the best rank of its children is 1. Now if you clearly see, which number should I choose? Which number should I give preference? According to this diagonal A of C, I should give preference to A because A is lexicographically smallest. So I would give the rank of this A. This rank of is A would be 1 for this diagonal. We are talking specifically rank about a diagonal. For this diagonal we have only one element, so rank would be automatically 1. For this diagonal we have two elements. This is the higher priority element, so we are treating as 1, and obviously this would be true. Now we are moving on this diagonal. So we start from here D. We have two things. It has two children. The first children has a rank of 1 and the second has a rank of 2. Which should I choose? Obviously the rank with 1. Obviously we should choose the rank of 1. So we would store something like D. We would store something like the rank of its best children would be 2. Would be 1, sorry. Similarly from here, infinity, and the rank would be 1. Yeah. Okay, let me just clean it up. It's a bit messy. Yeah, the rank of this would be the rank of 1 of this children and the rank of 2, the minimum of it is 1. So we are storing the best rank of the D. The best rank of its children is 1. Similarly we would do from here, the best rank would be 1 or either infinity. From this 1 or, now in this diagonal, after storing the best rank of its children, we would sort them. For example, if ADC is, automatically the first priority should be given to this because this lexicography smallest element. Now one may wonder what would happen if we have two B's over here, or the number of the same value, number of the same character. Which should I give more priority? In this case, the more priority should be given to that number. Like for this, the priority should be given to that number, that index which has a lesser rank of its children. Now the rank of this would be 1, this A would be 1, this would be 2, this would be, and this would be 3. Yeah, so the best rank of this B would be 1, we would be storing 1. The best rank of this B would be 2, so we would assign more priority to this B. So in this diagonal, what's the rank of this B? First A, second A, and after those A, this B should come and this B should come. Similarly, we would be doing for all the diagonal. What are we doing per diagonal? What are we doing? We are calculating for each element in a diagonal, we are calculating the best rank of its children. We are calculating the best rank of its children, and after calculating it, we are sorting them. The first criteria of sorting is lexicography is the letter like A, B. So we don't have to look the best rank of their children. A and B are sufficient. But if both of them are equal, B or B, then we have to look the best rank of its children. So yeah, this is the working of it. And one may wonder that if we have two B's and the best rank of the children will be 1 and 1, then yeah, we have to assign same priority to both of them. We can choose any of them. So now the question is, how would I reconstruct my answer when after doing all of those things and storing that rank? When do we create? How do we reconstruct? So for that reconstruction, we have to start from the start. Let me clean it up. Now, starting from this position, we have stored what we have stored: the best rank of its children. For every element, we have stored the best rank of its children. What is the best rank? This and this. The best rank is this. So we would move towards this element. Now for this, we have stored best rank of it. What is this? This or this? The best rank is this. Why? Because A is less than C, obviously. Now, for this, the best rank would be this or this. As mentioned above, this B has a greater rank as compared to this. Why? Because the best rank of this children contains an A, the best rank of this contains a C and a D. So the best rank of this B has a children. The best rank of the children of this index is greater than this. So we are assigning more priority to this, and hence we are choosing this. So we will be going towards this, after that this, and now the path. So that's why we are generating answer. That's how we are reconstructing the part. We will be moving towards this, and this. So let me summarize all of this, what we have done. Initially, before the answer reconstruction part, what we did is that we are grouping elements on the basis of their diagonals. And on a particular diagonal, what are we doing? We are computing the best rank of its children. The best rank of its children. And after that, we are sorting it. Now we are sorting in such a way that if alphabetically they are smallest, then that is given more priority. And if they both are equal, then we would see whose children has a less rank. And technically we would assign those priority in that way. Now, the answer reconstruction part is that what we have stored is A over here. What we have stored is the best rank of this children. We would move towards the best rank. So yeah, the best rank, and out of this has the best rank. This automatically has the best rank because A is higher in all these diagonals. Now this and this. Okay. So hence we would be generate an answer out of it, and that's how we do it. The time complexity of this would be O of n square into n log n, because we are sorting on this diagonal, and this diagonal would take, like if we are considering n elements, it would take n log n sorting, and the space complexity would be O of n square into, only n square, because we are just storing the order of it. Now we have minimized the space complexity. That time complexity of n square log n into n would give a TLE on Cses problem set, because it's not acceptable for that. What we could do, we could use radix sort to eliminate that in log n, that sorting in, not in n log n, in log n. Sorry, the radix sort time complexity is around O of n, so we are eliminating that log n part, and hence we are able to pass the test case. But the main motive was not to explain about radix sort, wasn't. The main motive was how we decompress that information and store it, rather than storing the whole string, how we decompress it, and that was the motive behind that problem. So I hope you like my video and explanation. See you in the next video.